Hello, everyone. My name is Inês, and I am part of the organization team of Deep Learning Sessions Lisboa. On behalf of our team, I'd like to thank you for joining us today in our first meetup on deep reinforcement learning. So just to give you a brief overview of how this meetup is going to go, Eduardo Pereira, which is our speaker for today, is going to give a talk for about 1 hour, and then we'll have about 15 minutes to answer all of your questions. So we kindly ask you to leave your questions in the YouTube chat so we can collect them and ask them in the end of the talk. So this is going to be the first of 2 meetups on deep reinforcement learning from Deloitte. And the second one will happen 3 weeks from now on the 17th of May. So just to let you know. So for today's meetup, we're happy to welcome Eduardo Pereira, a senior manager data science AI at Deloitte. And he'll introduce us some core concepts of reinforcement learning. And he will also explain how we can combine it with deep learning. So I'd like to thank you, Eduardo, for accepting our invitation. And without further ado, I'm going to hand the presentation to you.
Hi, Ines. Thank you. So thank you very much for the invitation for this session today. So as Ines said, today I'm going to try to give you an introduction of reinforcement learning. For this talk, I have like 3 main goals. So the first one is trying to be as comprehensive as possible because I'm going to give you introductory details about reinforcement learning, but during some part of the talk, probably it will get a bit deeper. The second one is tries to give you will look at this reference has a manual, so guidelines to understand the main topics of reinforcement learning. And probably you will also have a notebook that you are going to try at the end, very simple, at home. And the last goal is try to give you the insights also for the next talk that a colleague of mine will do it. So for the talk today, I think that the main motivation for this one is that the people that are doing reinforcement learning for a while, they try to mimic how human make decisions. So they try to learn to make good sequence of decision, acquiring as much information as possible through experience. And humans are pretty good on that. We also have this trial and error basis. We don't learn by examples, we learn by trying and error. So, and we have a very good perception of the world in terms of conscious and subconscious. And we are also goal-oriented, at least in our life. Some people more than others, of course. And there are so many open questions that some people in the literature also encompass, from neuroscience to psychology to machine learning, is how human behavior has been acquiring knowledge so far. So some guys say it's about evolution, so they're about the culture, experience, and so on. And so mapping question from this human perspective to the machine perspective is model learning an essential step to be learning before or in parallel with policy model. So in one side, I think we have the model, we're going to see what is that, and the other we have the policy. And are we able to learn the representation on their reinforcement learning with a very small amount of experience? We are going to see that reinforcement learning is very data-driven, okay? So I'm going to try to give you like a comparison between supervised learning that probably all of you already know, where you have this pipeline where you have the samples, you have an encoder representation and prediction. You teach by example because you have the human that gives you the annotation. And then you have a network, an architecture, a function, whatever, linear, non-linear, and what the type of machine learning traditional or deep learning. and then you will try to get the output, which is predict the correct level for the instance. So what you're trying to encompass here is the optimization problem, and it's also a generalization problem. While for the imitation learning, right now you have what samples from the environment, and you have some observation and actions that come from the expert. Already also you have the representation, and then you have the output. Probably in this case is a self-driving car, or it's an autonomous vehicle, or something like a mix between both. It's going to turn right or left, so the outcome is the action. In this way, we also have optimization generalization, but we also have some delayed consequences. Okay, so we don't have immediate reward. We are going to see what is the reward from the next actions. So I'm going to talk about that a little bit more. And finally, we have the reinforcement learning, which is pretty similar, but instead we have the reward inside the pipeline. Okay, so and we can see the data has a couple of states, action, next actions, and reward. So it will try to encompass all by itself. In this pie, we are going to see that it's like the policy or a key action state value. And right now, we have one more thing. So we have the exploration. Okay, and this is going to be important because, as I'm going to show you next, so optimization, the goal is to find the optimal way to make decisions. Delayed consequence is decisions that make an impact later. Exploration is something that you learn about the world to make decisions, okay? And the generalization is, in this case, is the policies, which is going to map the experience, the past experience to actions. I'm not going to get more in details about all the applications that are from reinforcement learning, because there are plenty of them. More of them you already know, because they are going to be very driven by games, especially. You have here some efforts from DeepMind as AlphaStart, the very well-known AlphaGo, and then OpenAI for the cubic, and for the Atari, so the famous paper of OQ learning approaches. And then you have some from some universities like Berkeley, which is also very, Berkeley stands for planning problems and controlling problems for robotics. Okay? So these are just some of the examples. For the real life, you have more and more applications on that. On DeepMind, you also have for the internal project that they do at Google that reduce the consuming energies of the ABAC systems, which is some of them. You have some of them that are also doing the medicine. So plenty of research and possibilities for reinforcement learning in real life. So in terms of the interaction loop, so the agents, they interact with the environment by following the policies. So you have the agent, you have the environment. So the environment, the agent contains its own states. You have a policy, which is normally called the brain. It has a value function that is a probability to some reward in a specific state. And probably, optional, you also have the model of the environment. And at each step, the agent receives the observation, which can be a state, if it's fully observable. You have the reward, and then the agent, the environment receives the action from the agent and emits an observation. So all of these to learn from make decision from interactions, as I told you, you have these four main topics. And the final goal is to select actions that maximize the total expected future reward. So to learn an optimal policy which maximize the long-term cumulative rewards. Okay, so you have to require to have a balance between immediate and long rewards, and then you try to have also like a strategic behavior to achieve high rewards. So this is an example where you have like a robot labyrinthic, where you have starting point, you have a positive value here in this cell, a negative in this cell. The actions, you can go up, down, left, right. The state is on each cell, see if it's occupied or not, if you have a wall like this one. And then the idea is like it should achieve as much reward as possible going through to this one and avoid this one. Okay, so if the model is deterministic, so you have like deterministic probabilities of having going from one side to the other, so probably you will choose the shortest path to go there. However, if you give a stochastic model, which the reward should be negative and it will vary, okay? So he will try to go as fast as possible to this one. So the shortest path as negative it is. And if you have a reward that is positive, so each time you go from one side to the other in the cells, so of course that probably he will see that as a good way to go. So probably he will go to the longest path. So instead of going to his final goal that is going here, he's going to try to going around because he's going to accumulate positive rewards. So again, the questions here and what we are trying to check in this talk is if what is the strategy to achieve the maximum reward. So if we're going to learn the model and plan, if we're going to learn the value of actions and state pairs, and act greedily and not greedily, and learn the policy directly while sampling from it. Okay. So this is notations that I'm going to go quickly, just to give you the understanding. Okay. So state is the information what is going to happen next. So it's a state of the environment. Is a complete observation. An observation is a partial one, so it's omit information. The agent and the environment, they have their own internal state. The environment can also be fully observable or partially observable. And the actions depend on the type of state, and you have an history that you keep track of the actions that you made. So you have like a tuplet of observation, actions, and reward. And so what we have more, so we have the trajectories. Some people's, in some nomenclatures, you have trajectories being the same as episode or as rollout. So if so, it's missing here the reward, but in this case, I'm putting here only one annotation. So what I have here is the tuplet between states and action. Okay, so in the initial state, it's normally randomly sample from distribution, and then you have the normal laws of an environment that can be deterministic or stochastic. This is also important, the reward and the return. So the reward is a scalar feedback signal. And the future reward, also known as return, is the total sum of discounted rewards going forward over an entire episode or over an entire trajectory. Okay, and you can compute this as a finite horizon on discounted return. So you have a temporal window, and then you will sum it, or you have infinity horizon discounted return. So you are going to have a discount factor that are going to penalize the rewards in the future. Okay, and it's going to be like exponential geometric decay. Okay, in this way you are going. And why is that? Because so you don't have pretty short if the future rewards may have higher certainty. So it's higher has the future, the higher the uncertainty, and the future reward may have no provide immediate benefits. Okay, so you have to have this discounting, and it's also mathematical convenience. So the value function is this is to have is associated to predicting the expected amount of future rewards acting by a corresponding policy. Okay, so if you are acting through a corresponding policy in a specific state, then you have the return accumulated from that trajectory. So, and you want to maximize that, so you want to pick suitable actions that maximize that specific actions, that specific reward. And then you can have different main functions. So you can have the onPolicies value function, which is giving a specific, so it's a state value. Okay, so this is the B value, is state value. You only have here the state over the policy. So giving a policy, what is the expected reward you're going to have on that specific state if you follow that, policy. And the Q function is you also have the state but action. So at the beginning you will follow, you will randomly select an action, and then you will see the state, and then you will follow a specific policy, and then you will see what is the reward that you have. These one are the optimals. So instead of so you want to follow, instead of some policy, you want to follow the optimal policy, and for that you are going to rant that you select always the best trajectory, the best action for that specific state. Okay. So the policy, it's also it's how the agents choose actions, and if it's deterministic, you have one action per state. If it's stochastic, given state, you have a distribution over actions that may take. So it's a conditional distribution of the state over the action. And you have this parametric model that can be adjusted to change behavior in optimization algorithm. So the model is the representation of the environment, and here I represent here already the reward. So you have everything. You have the transition, which is the state, the actual state, action, the reward, and the next state, and then you have these repeated until the terminal state. And the model has two major parts: the transition probability that predicts the next action state, and the reward function that predicts the immediate reward. Okay. Okay. Move forward. So in this case, if we want to formalize the reinforcement learning interaction, so again, which action is better or worse? If you have a reward function, which is the state and actions that are better, and the mathematical formulation of the R is a Markov decision process that is, I'm going to show you that these are the elements of the Markov decision projects, the Markov decision process. And again, if the environment is fully observable, so the state it's equal to the observation, and the agent is a MDP. If it's partial observable, we have a partial observable MDP. Okay. So here the future and the past. So the definition of an MDP of the Markov is that the future and the past are conditionally independent given the present. So the current states encapsulates all the statistics that you may need to decide the future. Okay. So and so to decide to predict the future, you only need to know the current state of the environment. Okay. So and this is a tuple that you have here for the reinforcement learning. You also have the reward, and you have the discount, and the discount factor is something between 0 and 1. And if you want to see this graphically, okay, so you have here the definition of the MVP. Okay. but before that, so this is already a Markov decision process, but before that you have a Markov process that is just the state and the transition probability, okay? So you don't have reward, you don't have action. Then you have the Markov reward process, okay, that you include the reward and you include also the discount factor. So when you have the reward, you can include the state value function that I told you before. In this way, you can have a trade-off intermediate and future reward. And when you have a Markov decision process, so you have all these tuples, okay? So you also include the action. So you have an action. That's why it's this decision process, okay? So when you have the POMBP, these emission probabilities, as I told you, is a conditional probability over those observations. And this is the representation that you have. So again, this is the representation of the trajectory. The spectral return is given by the calculus of the spectral return over the trajectory, and the ultimate policy is argmax of this computation. So regarding the anatomy of reinforcement learning, we have these three main blocks that I'm going to use to guideline the remaining of my presentation. So you can fit the model and estimate the return, you can improve the policy, and then you can generate samples, which means also run the policy. And you have a big spectrum of types of reinforcement learning algorithms, okay, which some are then better sample efficient than the others, and others are so less efficient and more efficient. So the model base, you have, we're going to get more details, but the model base, so you know the model of the environment, and you can use it explicitly for planning. And so you update this model and you replan often. The value base is you have a Q function. We cannot be explicit, which can also not have attached an explicit policy. You will try to act by using the best action state. And the exploration is like trying to find randomly, trying to explore randomly new interactions through the space. So it's a necessary add-on. The actor critics that I'm going to talk also a little bit more after, sorry, is a mix between the policy and the value. It's also is mainly used to improve the policy, and the policy space claims the stochastic policy function explicitly. So it acts by sampling the policy, and the exploration is baking in. So going from one side to the other, so you can have this kind of taxonomy of reinforcement learning algorithms. As I told you, so the model base you can learn, or the model is given, and if you learn is difficult, and you have different ways of learning. If it's model free, you have the policy space, so you try to get the deterministic outcome of sampling or sampling from the target policies to train the algorithms. Or if it's off policy, probably in a poly base, you would train over the distribution of the transitions produced by the different behavior policy rather than the target policy. So the challenge of deep learning, so all the things that I mentioned before are like functions, and this can be represented by different types. Where we are interested here is in the neural networks. And the challenge here are for planning. So, for learning first, so the environment is unknown, and the agent tries to interact with the environment. So the planning is when you give the model of how the world works. So you have the dynamics and reward models. Then you have the prediction, which is the evaluation. So you try to estimate, predict for the expected rewards for following a given policy. And then you have the control, which is the optimization. So you try to learn and fit the best policy. This is an example that I put here just to instantiate also what we have here enhanced with a real example, and also because this example that I'm going to show at the end, so it's very simple sample from Gene, is a control type environment. So you have here the description. So you try to attach this on active join to a card, which move along this track. The pendulum start upright, and then you try to increase or decrease the car velocity to the right or to the left. So these are the actions that you have here. And the observations that you are going to have is the car position, the car velocity, the pole angle, and the pole velocity. And you have the predefined mean and max values. In this case, you can see that the observations are continuous and the actions are discrete. You can also have a starting state, which in this case is the uniform random value. You have the reward, which is positive one for each step taking, including termination step. This V1 is because in Gene environment you have sometimes you have different versions, and this is the version number 1, so the threshold is 457. And then you also have the definition of when is the termination, how is defined the terminal state. Okay, so in this case, if it's the angle is higher than 12 degrees, or if the car position comes close to the edges of the screen. Okay, so far has been quite easy, I think, and it's going to be like the basis. This is also the basis, and it's also important to understand the Bellman equation, because it allows us to express values of states as value of other states. So this means that we can compute the value of the next state over the previous value of that state. So this is good for interactive approach for calculating the value of each state. If we know the value for the next state, so we can know the value for the current state. So more like this. So it tries to solve this MTP process to find the optimal policies and the value function. And what we have here is the matricial definition of the Bellman equation, where you have the value is you have one part that is the immediate reward, and the other you have this discounted sum of futures reward. When here you have the previous value of the state, and here you have the transition probabilities over the policy, and here is the discount factor. Okay. So if you interact over this, you get this Bellman equation that you can see that are the representation of this formula here. Just here are indexed by the policy pi. Okay, so you can have again the value, and then you can have again the Q function and the optimal values also. And so these are normally called the Bellman backup operators. So which can give you, which are useful because you can apply it to a value function or to a Q value. You return a new value function, or you return a new key value, and then you can improve the value or the key value of the key function, and then you have you can interact over all the states. Okay, so here you have an interaction process that can be explained by these two diagrams that are very similar. So one is a value interaction and the other is a policy interaction. So you start with a random initialization of the v value. You compute for each state the queue, you update it with a maximum value, and then if you get the optimal, you stop. If it's not, you continue and you loop it again. So and this is more or less similar, but here you have a random policy, okay, and you try to get first the optimal v value before improving the policy. And the other difference is that this one, it can be infinite or just when you converge, and this one, it's over key number of interactions. Okay, so sorry. So the idea of the value interaction is to compute the optimal value for an horizon. So the horizon is this key, how many interactions you want to use, and the policy interaction is the infinite horizon. So you try to select the best policy. So this is also interesting because the optimal policies for MDP, an infinite horizon problem, is deterministic, is stationary, so that does not depend on the time step, and it's not necessarily unique because you may have state actions with identical optimal values. So this is very important, is understanding this Bellman equation. So going for the model base. So in the model base, as I told you, is different from the model free because the model free methods learn directly from experience, while in the model base, what you have is a reduced number of interaction with the real environment. And during the learning phase, you have the information of the model, of the transition model, and the reward model. Okay. So an upside is that it can allow the agent to plan ahead. So explicitly deciding between the options, so he knows which is a better option. Of course, he knows the word. And the downside is that the ground truth of the environment is usually not available to the agent. So, and then you can have, if the agent decide bad with the experience that they have from the model, so you have a bias into the model, so that the agent can exploit and will behave suboptimally in the real environment. Okay, so in the learning, if you come back to the taxonomy that I show you, when you have this model base and it's learning the model, you can try to avoid this with some artifacts. So here the model base. So the idea is a planning problem. So it's a planning problem. We can introduce here the dynamic programming. Okay. So and the dynamic programming is so you can interactively evaluate value functions and improve the policies. So you can compute the the value function on each state, and you have this interaction between policy evaluation and policy improvement, which is defined by this pseudo algorithm. So you initialize the initial policy randomly for all the states, and while you have the convergence, you compute first the policy evaluation, and then you compute the policy improvement, and you interact, and at the end you have the final one that is the evaluation. So the policy evaluation, it allows to compute the value of the policy. It computes the fixed point of the policy for a particular policy. That's why you have the index I. Okay, and it gives an estimate of the finite horizon, as I told you. The policy improvement is monotonically improvement, and it tries to go to the optimal policy. And this cycle is what the literature calls as the generalized policy interaction. Okay, it says that by definition, right, since you're trying to get the best policy from the previous one, so it converges slowly to the optimal value. Sometimes it doesn't happen, as I'm going to show you that after with the policy gradient, because sometimes it can be stuck to zero when you do the learning process. Okay, just to finalize this model base. So you have different. So you have representation. Sorry I forgot to tell you this. So you have the representation of the model as a Markov decision process, right? And then you can improve the policy in several approaches, or you can fit or estimate the return because you can learn these transition probabilities. And then you have different methods that can encompass some of these approaches. So the analytic gradient computation is assumes that the form of the dynamics and the cost functions are convenient because they can yield like closed form solutions to optimal control. So in this way, you have these basic and simple control theories like LQR, dynamic analysis system, where you can compute these gradient-based approaches for policy improvement. So it's a pure planning. You have here the sampling-based planning, which it's trying to generate sampling distributions on action sequence. So it is important to generate candidate actions for the plan. For planning by sampling from its current policy. And finally, you have the model-based data generation, which tries to tackle the problem of generating, augmenting the experience. So sometimes you can have another reinforcement learning algorithm to train a policy or a Q function, and then you can try to augment this real experience with fictions, with synthetic data, or just with synthetic experience to update the agent. Okay, so these are like three types of algorithms that are encompassed here in the model-based reinforcement learning. So for the model-free reinforcement learning, so you have these two. So you have the value function and you have the policy, and then the value function is based on the value base, and the policy is policy based. So in the value base, you learn the value function, and you have an implicit policy, which can be its own greedy. In the policy base, you don't have a value function, so you try to learn the policy. And the actor critics is something that is in between. So you have an actor that tries to normally learn the policy, and the critic to try to learn the value function. And then this is, you don't need knowledge of the MVP, also of the complete definition of the environment. So this is unknown. Okay, so normally the value base are normally solved by temporal different learning that I'm going just to give a brief overview, and the policy space and actual critics are normally solved by policy gradient. Okay, so the first one, I will try to be simple here. So in this case, the model 3 in this type, the policy gradient methods, you update the probability distribution of actions so that the actions with higher expected reward can have a higher probability value of an observed state. Okay, so given a policy with parameter theta, you will try to compute the optimization with this gradient-based approach, or you also have no gradient, but normally it's a gradient-based. And then you have these normal functions for if you're using episodic environments, or if you are using continuous environment, or and then you can average the reward per time step. So here, the naive algorithms is that you propose now that makes direct use of the policies in order to learn the parameters. And improved algorithms can be like finding algorithms that improve the objective function in order to maximize the effectiveness of the policy. Okay, so what you have here is a normal, is an example of the normal stochastic gradient actions, where you try to search for the local maximum in the equation. And then you have the gradient policies, which is approximated by the expectation of the log over the policy of the Q and the traditional policy. Okay, so one algorithm that it's very well known, that is like vanilla, is reinforce, which is try to perform a trajectory rollout or an episode using the current policy. Then is stored the log probabilities and the reward at each step, calculate the discounted cumulative reward at each step. Okay, so this is the normal formula of the Bellman equation. And then it computes the policy gradient, which is this thing here, which is the new thing that we introduced here to do the optimization, and compute the policy gradient accordingly with the stochastic gradient agent and update the policy parameter, and then go back and repeat. Okay, so this is for the policy gradient. Okay, so here I'm just going to give you just a brief overview, because this is important, because sometimes in any model of machine learning you have the problem of the bias and variance. And in this way you can have different methods to compute the policy evaluation. As I told you, when you have the model of the environment of the world, so normally it's a dynamic programming problem. Okay, so taking the expectation over the next state, you consider the expectation over all the rewards. Okay, so you have the notion of the probabilities. Okay, and so going from this state to this state, you want to see all the rewards available. Okay, so that's why you have this information. So it's computed with the bootstrap. Okay, so the bootstrap is a future return using the value estimated previously, and so you don't sum up those lower downs to the potential rewards. For the Monte Carlo, what you have is an expectation over trajectories generated by following the policy. So the simple idea is just to have like a mean return, and so you need to go through the end of the episode. Okay, so you don't have the notion of what is, if its state is Markov or what is the next state. So you don't use bootstrapping. Okay, and what you have here is just computed with the learning rate, the reward of the trajectory minus the previous value. Okay, and the temporal difference is, it's a mix between both. So the key idea is that you have to have the notion of the next state, you have a notion of the reward. You compute this target TD, and then you subtract again using also bootstrapping. So you have sampling, you have bootstrapping, and then you are able you don't care about all the rewards, so you are able to go and check to what extent we want to update the value function, and these are like the main difference between these three learning methods. Okay, so again, so the key, so here the model 3 is the value function. So I already talked about this. It can be computed using the Monte Carlo or the temporal difference. I already mentioned so that the Monte Carlo learns from complete episodes, while the temporal difference doesn't need to go through the end of the episode. So the problem of the value functions for large MDP is that you can have many states and actions to store. So representing the value function with parametric function instead of with a table is not feasible. So you will try to use a function approximation, and this function approximation can be an artificial neural network, decision tree, whatever. And then you can have different advantages from being the most well known is using different kinds of architecture for neural networks. So I try to go faster here because we're running out of time. So the actor critics. So the idea is it's pretty simple. So the goal is to learn a value function in addition to the policies. So as I told you, we are trying to learn both. So the critics update the value function parameters depending the value function parameters depending if in type of algorithm is it's using an action value or state value, and the actor updates these policy parameters in the direction suggested by the critic. Okay, so this is the normal function that I mentioned before. So and here you have the return. So one of the things that are more difficult in the policy ingredients or the problems in the policy ingredients is the high variability. Okay, so it introduced during the training, it can deviate, the learning can deviate from many degrees, and also it can be stuck in a total reward of 0, so the model will not learn. So the simple idea here is to use a baseline. So in this baseline, it will try to be like a you will try to keep this more stable. Okay, so in this way, and the main baseline here, it can be the advantage value, which is just the difference between the Q function and the value. So the exploration and the exploitation problem here. So as I told you, it's important to try to explore the world, and in this way, the most common is the epsilon greedy policy. So it will try to randomly at the beginning select different actions. So this the probability it will be higher at the beginning of select random value, random actions, and then after a while, this learning rate, this epsilon will decrease because probably the exploitation usually will not more knowledge about the world, about the actions, about the reward. So probably you will have more close to the optimal decisions and optimal policy if you are computing explicitly the policy. And why this is important is important for all of them, but for here for the key learning, which is an off-policy TD. And in this case, what we want is to use again the Bellman's equations, and it's considering of policy because the Q learning functions learns from actions that are outside of the current policy. So you have random actions, and therefore policy isn't necessary. Explicit necessary to compute. And what you have here is the normal. So you have here the representation of the Q tables. So the Q table, it's a matrix of actions and states. And what you have in the normal, in the baseline, is that you will have you initialize the Q table with random values. You choosing actions to perform the current state. Then you receive the reward. You observe the new states, and you update with this function. And you have here some hyperparameters to optimize. One of these is the learning rate and the discount factor. And again, is so you're trying to it's a TD approach, okay? And then at the end you will find the new state. So you will replace the new state with the new state with the next state, and then you go and repeat through this step. So what I'm going to mention now is the DeepQ network, which is a representation of the Q learning approach for using neural networks. Okay, so you are going to try to use in architecture neural network in the simple way, and then you will try to surpass some of the problems that the Q learning has. Some of them is a memorization explosion that I mentioned before, and the instability and divergence when you combine the nonlinear Q value with the bootstrapping. Again, remember that you have the bootstrapping because you're using TD. Okay, so one of the things that you need to improve in the baseline model is in the representation. So if you use the convolutional layers, so you will have a more compact structural representation. So it's more, you are trying to generalize, okay? Then the spin replay, before that, you have the notion of the replay buffer, okay? So during each trajectory, you need to save all the spins in a tuple. So state, action, reward, next state, and then you will store it in infinite size cache. And this is the replay buffer. Okay. So and the spin is replaced. What is give you is that you can then randomly select a number of a mini batch from this buffer, and then it will improve the data efficiency and distribution, because the data will be more independent to each other, so it will be more close to the identical and independent distributed. So normally, so there are many variations of key network, but normally this spin replay is the one that has larger margins of improvement over the baseline. And then the other improvement is the separate target network, okay, which tries to give another target key value that are periodically updated to compute the loss for every action during training. So this is important because it helps to avoid this instability in divergence when you are training, and this is the main pseudocode that you have. So you initialize replay memory with the capacity. You also initialize the weights of the Q functions and the target Q. So you gather and store the samples in the replay buffer. You random the samples of experience through the replay buffer, so it's experience replay. And then you update the queue network. It has different meanings if it's terminal state or not. And again, you will repeat, okay? So then you have some variations. Has the dueling DKN, which tries to use the idea of the advantage function to compute the Q value. You have the double KNN, which is trying to calculate the reward added to the next state with the maximum key value using other network. You have the noisy DQN, which introduce noise in the weights of the network in order to try to mimic the exploration phase. And then you have the prioritized experience replays, which is tried inside within the experience replays, is try to see which is the most interesting batch of samplings to show before in order to the network converge quickly and faster and better. So as in conclusion, I think this is a wrap up. Okay, so I think that I already mentioned most of them of the advantages and drawbacks. So this is not exhaustive. Okay, and just to conclude, these are some of the research directions because of the problems that you have in deep learning. So it's a complex type of learning, type of algorithms in machine learning. You have plenty of information. And regarding the core algorithms, so what you see is that you are trying to looking for stability. So if your algorithm converge, how many runs, and if it's consistent, okay. So you try to minimize the fitting error, and you try to optimize the true objective, which sometimes in reinforcement learning is difficult to know which is a true objective. The efficiency, so how long it takes to converge. So for instance, if you go to the gene, I'm going to show you, you are trying to converge, which has with the maximum reward, but with the minimum number of samples. So in this case, you have a direct impact if you are learning off polys, of on polys, and of course the generalization. And the core assumptions of deep reinforcement learning. So it's a right problem formulations, how you are going to formalize correctly the problem to embed it into the reinforcement learning framework. And of course, if you want to put some kind of supervision, which is efficient source to use, and how you are going to evaluate. And of course, there are some people that are trying to use the imitation learning, okay, with side by side with the reinforcement learning, because imitation learning it's a good framework to give like expert knowledge with a complete tuple of information that you can use for your models. Okay, so and that's all. So I'm just going to show you quickly okay, so this is small example. So here you have, I think all of you know about the gene environment, okay, which you can find as an OpenAI platform, and you have many. It's a way to have a playground to have different environment and to test different models. So this is the main things that you have with the observations. You can get the observations reward if it's done, and some information for debugging. the information, the environment, you can load it, you can render it, and you can go step by step. And then you can, okay, so that's all. The other thing is that we use here, or I show you here, is the stable algorithms. That is another GitHub from OpenAI, which is a bunch of algorithms that you have that are implemented, and you have all of these. You can see all the information that you have. So you have different resources. You can customize your policies. You have callbacks. You have the TensorFlow integration also. And you can use the environments of Gym. So it's easily and ready to plug and play with each other. And finally, I'm also going to show you just the B suite that is from DeepMind. In this case, it's still is more close framework, but with a different goal. In this case, you have the idea is that you will design carefully experiments, okay, of reinforcement learning, and then you will have like a framework to measure and like a benchmark, unique and for all the type of reinforcement learning algorithms that you are going to have, and you have this radar chart where you can try to check the performance of your models, of your agents with the different metrics. So in this case, what I have here is very simple. So you have here the integration of the stable baseline with Gym and with B Suite. So in this case, again, is the carpool. This one, again, remember that the actions are discrete. So I have here some list of some models, some agents that can have that work with discrete action and others that work with continuous actions. And then you have here some functions are auxiliaries just to render something. And here you have the training where you receive the model class, the environment, and some functionalities to save some information. What I have here is very simple. So you instantiate the environment. So you need an extra environment, so similar to the one to get the monitor, which is like a wrapper, which you are going to use also for with a callback. In this case, what I'm using here is this one to give me information, to store information when you get a new base model while you are training. These are the normal instantiations, very simple, without any kind of optimization of the parameters, whatever. So I just instantiate the same policy for all the type of models. Here I just have this naive elif just to give you the explicit way that you can use the DKN with improvements to be with double DKN, with dual DKN, and with the priority experience replace. Okay, then you can learn it, and then you can serialize it. Okay, and then you have the loading, which is the opposite. You just deserialize it. You use this dummy vector environment to wrap your environment, and then this is the option if you want to continuous learning. Well, after you will evaluate, and this is the normal loop of the Gene environment. When you predict, you get the new step, you get the reward, you append the reward, and then you have the mean reward at the end of the episode. Okay, this is the integration with the TensorFlow. Okay, so here you have different algorithms, and then you have different scalars, and then you can also inspect the architecture of the different agents. Okay, this is to train. Here it's what I show you. When you can also use some functionalities to plot by yourself. Here I'm just plotting a smoothed curve, smoothing learning curve, or smoothing learning curve of the agent. Sorry. And then I get the evaluation. I have here the mean reward and the number of episodes. Okay, I didn't put any kind of sub criteria, nothing else. And here I have a visual debug, just the functions getting from the GitHub, which I can test and play visually if the model performs well or not. And then here you have so in this way I grab this continuous carpal version of the environment, and then what I put here is just a way that you can understand how are you able to customize or to create a new environment and then put it and then use it. Okay, so in this way it's the same carpal but with a continuous actions from -1 to 1, and then I have also the same follow-up. And finally, here you have the B suite. I don't go for it because you need to go more in details, because they have this CSV where they train different models for different agents, for different optimization process, and for different samples, and then they can grab some visual information to compare which are the agents which are best or not in so just to give an example here. So in this case they have the reverse noise experiment. So they put different seeds and they allocate a Gaussian noise for these seeds, and then they run the experiment, and then what I'm going to see if how these impact or how well the agents will behave with this kind of noise information. Okay. So yes, I will put this online also. I will read to the guys of the deep learning sessions Lisbon. Okay, so I think that's all for now. Okay.
Hi, Eduardo. Thank you very much for your presentation.
You're welcome.
We are now asking some of the questions. So the first one is from José Salvador. He asks, do we always need to identify what is a reward, or is there a way for the agent to create its own definition of reward? So
yeah, so you need to define the reward, yes, but you can also have some ways to try to estimate the type of rewards. Okay, so my colleagues, for instance, is going to talk about the batch reinforcement learning, or the offline, completely off policy reinforcement learning. And one of the things that is difficult in that approach is to understand what is the reward, because you are not training or you're not evaluating online. Okay, so you are not exactly what is the reward. Yeah, but when you define the formulation problem, it's better if you are able to know what is the state, what are the actions, and what are the reward, because it will affect your outcome.
okay, thank you. And the next question is from Ivo Pinheiro, and he asks, do we need to define all possible states? Can the algorithm discover new states with no reward previously defined?
Okay, so in the model-based approach, so the idea is that you define, you have the model of this transition, so you know exactly which are the states and which are the transition probabilities from actions to the different states, and you also have the reward function. I think that this question is pretty similar to the reward. So yes, when you formulate the problem, you need to know the states. Okay? You need to define the states. Actually, I'm not quite sure if the algorithm can discover new state, but I don't think so, to be honest.
Okay.
Because it will affect the way that you are even for the policy, or for the Q for the policy interaction and the value interaction, you need to know it.
Yes, very good. We have another question from Jose. He asks, after exploration, if the environment changes, how does the reinforcement learning types behave? I don't know if he meant algorithm here. Can they accumulate the changes incrementally and update policies, or do they need to start from scratch?
Okay, so Jose was the only one that was attending the conference, right? We have plenty of questions. Okay, after exploration, if the environment change, how the reinforcement type behaves? Is this a question, right? After exploration,
Yes.
change, how do the reinforcement learning type behave? So the exploration has nothing to do with if something changed. So the exploration is if you want to explore less or more, because you don't have knowledge about what is the interaction. So what is the outcome of your action in the environment? Okay, so they are not coupled. Okay, so you explore, the idea is that you try to explore at the beginning more than at the end, because if you follow a policy or if you follow a target implicit policy, you will try to converge, so you will get to the optimal, for instance. Okay, and so you start from scratch on each episode. Okay, so each episode you start from scratch. Okay, so from scratch, more or less, and so that's the way. It has nothing to do with exploration. Yeah.
Okay, very good. So here's another question. Now it's from Antonio Martins. Are continuous actions practically possible to implement due to computational efforts?
Yes. I mean, you have different. You can distribute. It depends on the type of the algorithms, right? So, so for instance, the DDPG, it's made on purpose to handle continuous actions. Okay, so yes, of course, that computational efforts, you have different computational effort in the reinforcement learning frameworks, and there are different ways to tackle. But continuous actions is some of the things that are tackled by different type of algorithms. Yeah.
So, so do you use like function approximation to handle continuous actions in opposition to the tabular setting on discrete actions? Is there a way to handle the continuous actions?
Yes, so you use function approximation when you have the explosion of the memorization or memorization. So yes, when you have a huge amount of state or actions, which is very difficult to put it all in the table, or just try to understand which are all the states or which are all the actions possible. You have this kind of a functional approximation that tries to give you more compact representation of the states. Okay, so going back to the other question of the quality that you're trying to find new states, so this is a representation of the state when you have too much of them. Okay, you will not try to find new state after.
Okay, so now another question is how or where is RL being used in real scenarios, or in particular at Deloitte?
So we are exploring reinforcement learning at Deloitte. In this moment, is a more research exploratory base. It requires a lot of background understanding, and we started with the basic elements, and we started exploring the most interesting frameworks out there, and right now we have a good understanding of what is possible, at least with some kind of algorithms. Okay, so we are not an expert. We are not working on this as defined for a long years. Okay, so this is something that because we have different challenge from our clients from different domains, and when you have a sequence of information or sequence of actions, so it's good to have this formalization of the problem. And what we are doing right now is so we are we're creating proof of values, okay, with small examples already have, even with synthetic data or with data that is available from simulators, okay. And we're exploring different types. I'm not going to tell you the type of use cases, sorry. But yes, so we are already using it for proof of concepts to show to our clients.
Okay, very nice. And one last question from Jose. Which techniques of reinforcement learning are better suited for real-time learning and planning?
Say again, sorry.
Which techniques of reinforcement learning are better suited for real-time learning and planning?
Okay, so planning, it's optimal control. So it's optimization. So again, you have to see if you are looking to try to explicitly compute the policy, or if it's enough for you to get instant if it's okay for you to have the instant reward for each specific state, and then do some faster analysis. So it will depend. So I in this moment I don't have enough knowledge to tell you so which is the best from all the big type of reinforcement learning algorithms that are out there, which is the best one for this. Okay, so but for sure it will be between the value and the value base and policy base.
Okay, so that's it for the questions. Thank you very much, Eduardo, for your presentation. Thank you. We'd just like to remind you that the video is going to be online on our YouTube page, and that the slides as well as the notebook that Eduardo showed are going to be available on our GitHub page. So we kindly ask you to fill out the feedback form. The link is available on the video's description so that we can improve our meetups. And lastly, if you work in deep learning and you'd like to present your work in one of our meetups, you can also fill the speaker application form, which is also available on the video's description. So thank you all for participating. Thank you, Eduardo, once again, and we hope to see you soon. Bye-bye.
Thank you. Bye-bye.
Bye-bye, everybody.